Hello, good morning. To the audience, please, if you can hear me, mm, let me know in the chat, please. Okay, perfect. So, good morning, everyone. Thanks for coming. And today, my goal is to talk about SciPCAD and focus my attention in some elements that we can use in the program SciPCAD, and these elements are pre-stress elements and post-tensioned elements. We will talk about the different kind of slabs within we can apply the post-tensioned cables. So this is the example that we will develop in this session. It's a very simple example, only with the goal that permit us to show the workflow and the different options that the user have when they use the program CypherCAD and the different options to modelize the post-tensioned elements. So we will start with a new project, a new job. To do so, we will go to the file and the menu file, new, and we will define the name of our job. We choose Donka. So a name, in this case, we will use the empty project way to define our model. We can accept here. And this is the main menu that in general the software will show at the beginning of the definition of a project. Here we can define the different codes that we'll use in our project. For every kind of material, we can choose the necessary code to apply for our job. In this case, we will use the American codes. After to choose the different codes, we can also choose the different kind of material from different lists. In the drop-down menu, we have a list with different type of concretes. These concretes are existent by default in the program, but the user can also define his own concretes. For example, here the user can define the name for the concrete and the specific characteristics or features that the user needs to define for the project. After that, the user have available this concrete in the drop-down list. For this case, we will use a concrete of 300 for the floor slabs. You will see that the frames and the different dimension of the slab will be not the traditional one, but most important that in general we use in a traditional concrete reinforced concrete building. So it's important to say that we can also define the foundation in the same project. So in order to define the kind of soil that we will use in our project, we can go to this little button. In this button, we can define the soil resistance with a geotechnical test or a geotechnical study. We can obtain the value, and the user can type this value in the different cells. But the program have a list with a different type of soils and the most common values for the resistance for this kind of soils. So it's interesting information when the user began with a project and don't have the values from the geotechnical study. for the first try or the first test in a project, the user can use these values and to have an approximative result. We can accept here, we can cancel, and after that we have the possibility to choose the different kind of steels. So we choose the grade 60, and this very little button, but I think the most important ones in our CyPCAD program is by position. Here, the user have the possibility to define different configurations and to take different options in order to adapt the results and the different combinations that the program can use at the time to design the different elements. So you can see that the program offers us in a classification of type of elements, for example, columns, walls, floor slabs, foundation, beams, slabs, and mat foundation, footing, etc. Different buttons where the user can redefine the different, for example, the different bars that the programs can use at the time to design a column. For example, here the program will use the number 4, number 5, number 6, number 8, and no more elements from this list of longitudinal bars. For the transverse elements, the stirrups, the user for the columns will use the number 3. If the user wants to use, for example, other diameters, and that other diameters will be available in the design of the element, the user can check this option and accept, and in this case the program will use the number 4, for example, for the transverse reinforcement when the design of the column arrives. So after that, after the definition of the codes, materials, and different options, we can also define the sections. In this case, we will not use the steel sections for our example, but it's interesting to know that the sections in steel can the material can be chosen here from a drop-down list, and the kind of steel, the type of steel may be defined by user in the same way that we have been see for the concrete with steel by user definition. After the definition of the materials, the user can also apply different loads. For example, for the wind load code, we have this available, the American codes and some local and national codes too. For the seismic loading, same way, we have a list of different national codes, and in this case, we can also apply for the American codes, different codes, and the ASCE code or the UBC, the IBC. So the user have different options in order to apply the seismic load for his project. In this case, we will apply this option for our examples. Remember that we will focus the attention in the post-tensioned and pre-stress elements. So after to accept the main menu for the general options, general data, we have here the workspace. So the steps to define the step to follow in order to define an structure in CypherCAD is indicated by the order of this sheet: column definition, beam definition, results, contour maps, and health and safety. In general, we will use for an structural analysis the fourth sheets: column definition, beam definition, results, and contour maps. So with the in the column definition, in the sheet column definition, we will define the first step for the geometrical introduction data is the definition in the vertical geometry. So we will go to introduction, floor groups, new floors, and we can define the single ones, and we for our example we will use 4 different floors. Same 8 for every floor, for every group, and lip load and dead load that will be applied on all the surface of our project in every floor. So we can define 2.0 kilonewton by square meter for every floor. Remember that is only an example. The focus is the definition of the post-tensioned elements and the use of these tools in the software, the analysis, the check of their different results, and the obtention of the different documents at the final of the project. So we can accept here, and we will position the different columns, the different vertical supports for our project. The geometry will be very, very simple. So we will go to the introduction, columns, shear walls, and stars, the new column. In this case, you can see the menu. We have the reference for the column, the final group, initial group, and some different options or different features for our columns. In this case, we will select the four floors. We can select the type of section. We have the user have the different option for the sections and the material. We have the reinforced concrete, the steel, timber, a composite section, and a generic section. And for every kind of material, we have different options too. For the kind of profile here, for example, or different combination of reinforced concrete and steel combined in a composite section in different ways. For example, for external concrete reinforced or external steel and reinforced concrete inside. So for our project, we will use the first option of materials, the reinforced concrete, and we will use the most simple element, the most simple geometry for our column. In this case, we will define 50 by 50 centimeters for our square column. We can accept, and we will use the virtual axis that the program offers us in order to obtain the position of the columns. So I will position the mouse in the X axis, and the program will offer me a menu when I can tape the exact value for the distance between the two columns. We can tape the distance and enter to accept the distance. So I will do the same to obtain the 5 columns in the X direction for our project. And in this case, the same way for the Y direction. Here we can see that the program create the different virtual axes, and we can use this new axis or the new cross to obtain the position of the next columns. So here we have the geometry for our example. We can pass to the next step, that is the beam definition. So in the program, in the CyPCAD program, we will define floor by floor the geometry of our slabs and the perimeters to define. So the first step is to define the perimeter. To do that, is necessary to introduce beams or walls. For our example, we will use beams. In the first floor, we will use slabs, different kind of slabs, and this kind of slabs have the possibility to be combined with post-tensioned cables. So for the first floor, we will use the flat slab, and to define the perimeter, we will use from the family of different beams the limit non-structural or limit beam, in this case the width 0. So we can accept here, and we will see the different ways to define the position of a beam. So the user can use different ways in order to obtain the position of a beam. So we can obtain the geometry from, for example, an EFC or a beam philosophy, a beam way to define the geometry in vertical and horizontal too. We can also obtain some plans or layout or drawings for the architectural project, and obtain with different reference the position of the beam. And I think that we have some different videos in our YouTube channel with different webinars or demos that demonstrate that. And in this case, for our example, I will use like reference the columns. So to obtain the position of a beam, in this case a limit beam, I will approach to the first column, C1. You can see a red point, and we will use different tools or different options available in our program in order to obtain the position of the beam. So the first point or the initial point for my first beam is the center of C1. So I can go to the final point in the center of C5. This is a way to obtain the position of the beam. But our slab will be positioned at the external limit or our external face of the column. So to adapt this limit to the external position, we have a tool in the program that is called adjust. We can go to adjust to modify the position of the beam, only position the mouse at the external point near to the middle of the beam, and clicking there left, the position of the beam will take the external limit of the columns. You can see that it's very, very simple, very easy. We have other possibility to define this position for the beam, and I will show for the next one. It's the previous configuration of the position of the beam at the left, center, and right, and that have relation with the direction of the introduction of the beam. For example, in this case, I will choose the left position for the beam, and we can obtain this position for the beam at the external perimeter of the building. When a perimeter is closed, the program will offer us a definition of a slab, and we can go to the menu slabs, to the panel manager, in order to define the different type of slab that we can define in our project or use in our project. In this case, we will go to the panel manager, define panel, and we have here different kind of slabs. So the joist floor slabs, hollow core slabs, composite slabs, waffle slabs, flat slabs, mat foundation, and awaiting definition. Awaiting definition is the default slab that the program introduced when the perimeter is closed. So for the joist floor slab, we have the the 6 of different joists that the user can uh, option or use in a project. So we have the precast elements, and in this case, reinforced joist floor slabs is a precast element, but they don't have an pre-stress or post-tension element. In this case, the second one is the pre-stress joist floor slabs. Obviously, it's a precast element, but in this case, it's a pre-stress joist floor. The third one is an in situ joist floor slab. This kind of joist is available to apply an post-tension cable or post-tension element. So we will use this kind of slab for the third floor or the fourth floor. After that, we have the steel joist, so the profile, the normal profile or the market profile, and we have the open web joist floor slab and the timber one. Okay, so after that, we have this kind of slab to define. The user can introduce the characteristics of the manufacturer, the local manufacturer have for the series of the different geometries for the hollow core plates. And the user can define these characteristics, these features, in order to obtain the results with the program. Once that the user have defined these characteristics, that comprises an library, and user library that will can be used for the futures and the futures projects. We can cancel here and we can go to the composite slabs. Here we have the form deck and the composite deck. We have some different kind of elements. The user can modify these elements and that appears by default in the program, but the user can also define his own elements and his own geometries for the local market or for the local manufacturer that is adapted to the local or the position of the project. So this next kind of slab is the waffle slab, and we have here two different kind of waffle slab differentiated by the form of the form. Okay, so the kind of form may be a lost form or a removable form. If I choose the removable, we can see the different form. It's a plastic in general form that we is recuperable at the end of the precast and elements. So we will go to use in this case the lost and this kind of slab is available to apply and post-tensioned cable or post-tensioned tendons. We will use this this geometry for the second and third floor of our example project. The next kind of a slab is the most simple one, is the flat slab. We need only to define the depth, and we will have an reinforced reinforced bar in two directions, two perpendicular directions. We have the mat foundation too, and here we have the user need to define the depth and the soil resistance and the subgrade modulus in order to obtain the matricial model. So for our first floor, that is the floor that appears here in the floor 1, we can define the flat slab. We will use 25 centimeters for our depth. We can accept, and to introduce this slab, we need to click inside the perimeter, and after that, the program, you can see here in the left, in the bottom of the screen, select the beam to establish the direction of the reinforcement. That is interesting with the user use different options or different orders that that him don't know the order to the clicks or the different options. That is an interesting help to see if an option or an element of the program it's hard to use, or if you don't have the step to follow. In this case, the program show us that we need to select the beam to establish the direction of the reinforcement. So we select a beam, and we have a parallel direction of the reinforcement and the perpendicular one. So we can see in the 3D view the advance of our example. Okay, so after to apply the introduction of the slab, we will apply the post-tensioned tendons or the post-tensioned elements. So we will go to the post-tensioned menu. We have here the menu with different options. We can see that there are the first menu from this column of options are the general characteristics or the general features that the program will take into account at the moment to define a tendon. And these are some values that are defined by default in the program, but the user can modify this value in order to adapt his criteria for the project. We can have here the different distance, minimal distance, maximal distance, and different percents of the tension loads. We have here the default settings, and we if the user modify these values, can save these personal values like a default setting for the next project. So to obtain the different menus, we can go to the next step is introduce the tendons. So we have two options to introduce the tendons. We have the concentrated tendons, and we have the distributed tendons. So we have here the introduced concentrated tendons, and in this menu, the user can define the number of tendons that the group of concentrated tendon will have. In this case, for example, by default, we have 4 tendons for the group, and the user can define, for example, the position of the initial anchorage with an angle or a distance to the top surface. We have two kind of stressing anchor and of anchorage, the stressing one and the dead anchorage two. So the user can define if an anchorage have a type or another type of function. So this is for the anchorage. The next step, in this case, I have some values from the library, but in general, these values are empty. So the user need to go to this menu in order to define the tendons. The tendons may have a reference, need a reference, really. The user can choose if the tendons are bonded or unbonded. We have the number of strands for our tendon, the strand area, and different values in order to define the characteristics or the features of the tendon. We have a list here with the different tendons that are defined in the project. We can export the tendon if the definition is a new for us, and we will and this tendon will be available for the next project. If we have a library, we have the possibility to import the different tendon from this library user. If I want to define a new kind of tendon, I can go to the menu New. For example, here I can choose or type a reference. For example, here the T2, and this I will complete the reference with T27, and the number of strands in this case will be 7, for example. And we need to complete the other features for our tendon. So we can accept, and after that this tendon will be available to be applied in our project or our slab. So for the introduction of the tendons, we have the general job parameters. Remember that we have this definition at the first step of our menu. So the introduction that we will do is following the general job parameters, but we have the possibility to define particular tendon parameters for the different position of the groups. In this case, we will use only general job parameters. So I will accept, and we need to define the post-tensioned introduce concentrated tendon, insert the first point. So we need to define the first point of the axis of the group of tendons. I will use the reference, the cut reference, and I will position the tendons in 3 files for our project. At the middle of in the middle of the group, we can see this green line. So this green line is an flexure line. This flexure line will be important in order to define the different position of the tendons. In general, the flexure lines will be coincident with the line of supports. In this case, for example, the columns. So when a flexure line appears and a tendon cross this flexure line, the position, the natural position of the tendon will be at the bottom of the slab. Okay, so that will be very, very important in order to obtain the position of the tendons and the application of the forces of the post-tensioned cable. The next step, and that will be applied in our example, will be the use of the distributed tendon, and will in the X direction, I have already applied the group of tendons, and the other direction will be applied the distributed tendons. To do so, we can go to the menu. In this case, we have a very similar menu. We have the initial anchorage, final anchorage, the type of tendon that we will use, and the general job parameter and the layout. It's the different position that the tendon will adapt when the initial, final, and flexural lines appears. But in this case, we don't have a group of tendons. It's only a separation between tendons that will be defined. For our project, for example, the separation between tendons will be 1 meter point 60 centimeters. So we can accept here. We will take this point like reference. This is the direction of the tendons, and we will define the area where the distributed tendon will be defined. So you can see that every tendon in the area will be applied in this way. So it's important to see that every tendon have a different reference for example, the anchorage. If it's the anchorage is a dead or pre-stressed element, the form to represent the element will be different. We have here the different signs to in order to difference the kind of tendons. Remember that we have applied here the same kind of tendon, the T1, for all our tendons in the slabs. So the design is the same for everyone. And it's important to remark that a red circle appears. This red circle remark that a clash between two tendons is detected by the program. So if we can see that here in the 3D view. As you can see, the physically the tendons are crossed and coincident in the geometry for the slab. This is is something to avoid and correct by the user. So in this case, for example, the user needs to modify the layout for the group of tendons or for the distributed tendon, at least the initial ones, in order to avoid this class. It's important to know that the program will carry out or make the analysis without problems. Indeed, this error or this remark appear, but is something important to avoid in the reality of the project. Okay, so we can see, editing the tendon, the layout that the tendon have for from the initial point or the initial position to the final position. And we can see here that the layout of this tendon is not correct, because the position in the middle of the slab is the bottom of the slab, when we need here that the position of the tendon will be at the top of the slab. So here we need to apply the option or the tool, the introduce the tendon flexure lines. You remember that the group of tendon at the time to define the group of tendon, and flexure lines appears in the middle or in the axis of the definition of the group. And this is very useful when we can see this tendon, when we can see that here the flexure lines appears, and these lines will influence the layout of the tendon. But in the case of distributed tendon, there are not a flexure line automatically defined. So it's the user that need to introduce the flexure line coincident with the different direction of the supports. We have here the flexure lines, and we can edit the tendon, and this is the suitable behavior or the suitable layout for the tendon in the top of the support positions. Okay, we can see that in the 3D view. So we can see when we edit a tendon that the forces that will be applied for our project appears here, and these forces will be applied to our slab, like a load case. So we can go to the 3D view, but not only for the first floor, but for the whole project. We can go to the next floor in order to define first the waffle slab, is the other type of slab that available to apply post-tensioned tendons. And in order to define this waffle slab, we need to define the first step is to define the perimeter. Generally, the kind of beam that we use to define a perimeter of a waffle slab is a flat slab, a flat beam. Sorry, this flat beam will have, in our case, 25 centimeters, the same height, the same width that the width and height. We can accept here, and we will use the same way to define the position of the beam in reference with the supports, in this case columns. Easy. So the perimeter is closed, we can go to the slab menu, panel manager, and define panel. So in this case, we will apply the waffle slab. We have a library, and very important library of this kind of elements. We have, for example, this one, the most important features for our waffle slab are the distance between the ribs, the dimension of the rib, and the height of the form and the compression slab. So we can accept, and as we have already done for our first floor, we need to click in the perimeter, inside the perimeter, and we need to click on a beam, and we will have the direction of the ribs, and we can redefine the insertion point. In this case, we will take this point and redefine his position in order to define the tendons in an easily way, and this point will be maybe applied, for example, in the reality of the project to take into account to define the position of the ribs to apply the reinforcement. So this waffle slab have not only this area of ribs, but he need this slab need to the drop panels. We have a tool that generate the drop panels automatically with an interesting user default selection. So like that, we have the area of the forms and the massive area near to the support in order to resist the punching shear. So we have these elements, but will be we can apply here the post-tensioned cables. So to do so, we will go to the menu post-tensioned options. We have the layout here. We can go to the introduce the tendon flexure lines, introduce concentrated tendon, and introduce distributed tendon. In this case, the option, the correct option is introduce distributed tendon. And I will introduce here. Remember that the slab, the panel manager, we can see that the slab have the ribs every 80 centimeters. So we will apply the distributed tendon with 160 centimeters. So every 2 ribs. we will use the T1. We can accept here. We need to define the direction of the tendon, and the second definition is the area where the tendons will be distributed. So you can see that every tendon is coincident with a rib. Okay. So we can go to the edit tendon, and the user can verify that the layout of the tendon is not the correct one. Remember that the user needs, in this case, to introduce the flexure lines. In this case, we have a flexure line here because it's the initial and the final position, but we need to define, in this case, the flexure line in the middle, coincident with the line of support. So we can verify that the layout of the tendons now is more approach with the suitable disposition. Okay. So for example, here that something that I will try is to define this level of the floor with the waffle slab, applying tendons in one direction, but in the next one I will use an option from the program that is the copy from another group, and we copy all the different data from the second floor to the third floor. And in this case, the change that we will apply in this third floor is to apply the post-tensioning cable in both directions. Here we will apply not only in the y direction, but in the x direction too. And we will see the difference in the results. We can introduce distributed tendons the same way that we have already used in the second floor, and like that we apply the post-tensioned cables in both directions. We need to verify that or check. We need to check that the position and layout of the tendons are correct. Remember that we need to define the flexure lines. In this case, you can see that the layout is not the suitable layout. So we need to introduce the flexure lines. We can help us ourselves to define the position of the flexure lines with the reference and following the line of the supports. We can edit the tendon, and now the layout is the correct. Okay, so remember that the program remark the different class between two cables in a physical reality, for example here. So the user needs to avoid or correct this class. The analysis will be finished, no problem for that. But the reality of the cables in the project need to avoid this problem. So the other kind of in the next floor, the other kind of slab that is a potential slab where we can apply the option for the post-tensioned cables or post-tensioned tendons are the joist, the in situ joist slab. So to define this kind of a slab, we can go to the next floor. We need to define the perimeter, and in this case, we need to define a beam here in order to obtain the support for the joist in that will have in this direction, Y direction. So for the beams, we can go to the menu beam. For example, for the secondary beams, we can apply, for example, the 25 centimeter of width and adapt the height to the slab, to the slab depth. And for the for the principal beams, we can we need to use the drop beams. In this case, we have a width of 30 centimeters, for example, and 45 centimeters of depth for the external beams. And for the internal beam, we will modify the depth, for example, 55 centimeters, and the position of the beam will be at the center of the axis. Here we need to approach the center of the column, and we go from the initial point, the first one, to the final one. We don't need to define the beam point by point. That is not necessary. The program will detect the class or the cross with a support, and the program will understand that is a continuous frame, and there are a support there. So we have here in this floor, we have already defined two different perimeters. So we have said that the kind of slab that we need to define here is a joist slab, and the kind of joist slab that we can use with combined with post-tensioned tendons are the in situ slabs, the in situ joist slab, sorry. So to define the geometry of the in situ joist slab, we need to define like first step, the form of the element, the principal element for the lightweight. So in this case, we can go to define the name of the form. We can choose, for example, a name that help us or help the user to difference the type of form that is defined. In this case, 25 the depth, and poly is in reference with the type of form, the material. We can define, for example, here the kind of form. We will see that, and here we can define the compression layer thickness and the rib spacing. So first step is to define the form. We can create. We can go to 25 poly, and we have here the type of form, and in this case we will use the different dimension of the form to define an rectangular form, not with this form, but a rectangular one. To do that, we need to define the dimension A, C, and B with the same width. So we have here, for example, 85 centimeters, 85 centimeters, and 85 centimeters. And we can see that the form of the geometry, the pattern of the form are rectangular. And we can define and write a spacing of 100 centimeters. So the rib will have a dimension of 18 centimeters of thick. So we can here we will add the compression layer thickness like a reference. We can accept here, we can accept here, and we can click inside the perimeter and click on the beam. With clicking on the beam, we will adapt the direction of the axis of the beam like the direction of the first joist. So the joist will be parallel to this beam. We can change the insertion point and we can go to the neighbor panel to copy panel, and we can ensure the continuity of the different joists. We will have a continuity of the stress and forces. But in this case, we need to apply the post-tensioned tendons. So we can go to the menu post-tensioned. We can go to the distributed tendons. Remember that the axis, the separation distance between the ribs was 100 centimeters. Type of tendon is T1, and we need to define the direction of the tendon, initial point, final point, and the area. And every rib will have, in this case, a tendon. So we can go to the 3D view in order to check the state of our project until this moment. In the 3D view, we have different possibilities to observe or to select different portions of our project. We have the possibility, for example, to move the camera like an observer. In this case, we need to push Control and Shift and the wheel of the mouse. Like that, we have the camera like an observer. Okay, here like a leaf with the mouse, and when we have in the position of the floor that is interesting for us, we can observe the 3D view like a real observer in the building. Okay, so we have already defined the project. We need to save the project, and we can launch the analysis and design of the project. So I can see that there are some questions. Maybe the questions we can try to answer the question at the end of the presentation, or maybe we can take note of that and answer the questions by mail after the presentation, because I think that will be a little long. So at the end of the analysis and design of the project, the program will present us a report of different checks or different details that we need to check or revise in our project. So in general, we at the end of the analysis and design, we need to go to the third sheet, is the results. And we have here, I think, the most useful tool in order to check or understand the behavior of the building of our project for the different load cases or combinations. Is the deformed shape. We can here go to exaggerate the scale factor of displacement. I like to have this option, because like that I can see the deformed shape with all the details, and we can also see if some elements are disconnected or there are some weakness or non-suitable behavior of the building for a load case or for some loads. So in this case, for example, we can see the deformed shape for the self weight, and we can add the waffle and flat slab, the finite elements for the web discretization for these elements. We can see, for example, remember that we have here the flat slab, waffle slab with one direction, with two direction of tendons, and here we have the joist, in situ joist slab. Okay, so we can, for example, go to, and this is important, the post-tensioned instantaneous losses and total losses. This load case is interesting to see for this example. We can see the action of the post-tensioned forces. Remember that for the first floor we have an distributed group of tendon, distributed tendon in this direction, in Y direction, and only a group of 4 tendons in the line of the supports in the direction, in this direction. We can, for example, go to the we can see, for example, only this slab. We can exaggerate the factor, and we can see the application of the forces of post-tension. We can go to the next one, floor. In this case, we will remember that we have only the distributed tendon in this direction. So we can see that the forces applied have an important, very important influence in only one direction of the slab. But for this next one, we have a distributed tendon in both directions, and we can see the effect of all these forces applied on the slab. Remember that we are observing only a simple load case, so we can also see the select combination, simple load cases, or displacement. Okay. We can see the next one. In this case, we have the joist slabs. We have the possibility to determine the maximum value, for example. Okay, in order to see the instantaneous displacement for the different load cases, and self-weight, etc. And we can add on superpose the structure in a different kind of perspective and projection. Okay, so here for the deformation shape, and we can check the results in order to, for example, we can start with the first floor. We have here the flat slab. We can see that the different position of reinforcement are designed for the slab. We can obtain all the drawings for these armatures. We can, for example, assign a base reinforcement for this element. So we can, for example, apply for this one and and reinforcement basic, and we can go to flats, match reinforce, and we can redesign a slab. The program will take into account this base, this armature base, and we can see only the reinforcement. That may be interesting in order to obtain and more easily positioned armatures in the reality of the project. Okay, so you can see that the reinforcement are more clearly defined. We can go to the views, for example, and see only, for example, the longitudinal and bottom, and we can see that the is much more easily defined for the reality of the project. A very important check for this kind of slabs are the punching shear. That is important to remark because we have two ways in the program. We have two ways to check the punching shear. The first one, and this is the applied. This is applied by default for the program. Is the tangential stress check, the most basic one. In this case, we can see that that appears some reinforcement for near to the support, near to the column, and we can, in this case, all the checks pass, but we can also apply the method that the code suggests. In this case, for example, for the American code, we can go to the check, and some of the checks applying the code don't pass. So with the program, we can generate a reinforcement. The user can apply a reinforcement with inclined bars at 45 degrees, or the user can define the bind type reinforcement. To do that, we need to go to this menu view. We can define reinforcement shear. We need to apply a name for the reinforcement. The width of the beam, for example, 40 centimeters. The longitudinal reinforcement may be 6 longitudinal bars of, for example, in this case, the diameter of 4. The layout will be, for example, with different stirrups. The user can define his own layout, for example, like that. We can accept. After that, we need to define the transverse reinforcement. We have the layout, but we need to define the stirrup diameter. For example, here we can choose the number 3, the crossed diameter number 3, and the reinforcement spacing of 10 centimeters. So we can accept here, and we can apply this reinforcement for this support, for this column. The program have already applied an reinforcement for the stress, the classic check. So we need to go to the waffle slab and delete this reinforcement. We can go to the modify reinforcement, tangential stress reinforcement. We can delete group. Okay, we can pass to the punching share, and we will apply for this support the method of the code. And we can go to the check, click on the support, and we can see that all the checks from the code pass. We can obtain the report in a PDF. In a PDF format or different format. We have the XML, we have Word format too. But the important thing is we have a very complete report in order to communicate the result of our analysis and our design. And this reinforcement will be applied in our can be applied for different supports. For example, we can assign reinforcement, for example, for different elements. Remember that we need to delete the tangential reinforcement that the program applied with the classical check. We can delete group, and for these supports, apply the punching share reinforcement and the punching share checks from the code, obtaining at the end the complete report of all the checks. And we can obtain all the reference of this reinforcement in the drawings too. We will see for that at the end of at the final of the presentation. So we can go to the next floor. We have here the different reinforcement for the waffle slab in the same way that we have in the lower floor. We have here the possibility to see and observe the different reinforcement position of the element, the top coincident with the line of the supports, and here at the bottom. All these elements will, all this information will be available in drawings that we'll see in a moment. we can see the difference between the, for example, here we will go to see the view for the transverse elements 2. And we can see the difference between the two the application of the two webs, different webs for the tendons. Remember that in the second floor we have only only a distributed tendon for one direction. You can see that we have a very important reinforcement here for some elements, and you can see that we have less reinforcement in the second floor of waffle slab. The program have already taken account the forces applied by the post-tensioned tendons. For the next one, we can see here the different in situ joist. We can see the reinforcement at the bottom and in the top of the ribs. We can see that the checks of the joist, there are no errors when the distance between the supports are very, very important, and we don't have here errors or deflections. Thanks to the cables and the post-tensioned tendons. It's important to know that for the different slabs we have some interesting tool in order to obtain the information of deflections. So we can go to the contour maps, and here we have the tool deflection. We have here the contour lines, the values of the contour lines. We can see some points when where the deflections are more important, the formation are more important. So we can check this area with the tool deflection. We can click in 2 points, and the program will show us the information of the deflection. In this case, for example, we can see that the deflection is not important, or it's under the limits of, in general, the codes suggest. Yeah, this tool is very interesting too, not only to obtain the information of the deflection, but also to obtain, for example, information about the integrated forces of our slab. In this case, for example, I can define a strip width, and the user can, for example, go to the menu forces, obtain, for example, select, for example, the moment X, and we can see, clicking in different points, an integrated strip of forces. So we have the possibility to obtain with these values values that serve to check by hand, or for example with others programs or applications, the reinforcement designed by our software. It's interesting to see like that too, how the forces change in the different direction of the slabs. For example, here we can see the forces for the self weight. We can see how the distribution is, and we can, for example, go to the post-tension total losses, and we can see the different direction of the forces for the application of post-tensioning stress. Okay. May be interesting in this case to compare the stress and the forces applied by the self weight and the stress in order to apply a criteria to, for example, have an order of how much of the self weight of the slab may be equilibrated by the forces applied for the post-tensioned elements. So we have already seen that we have the possibility in the program to obtain some reports. The next step for a user is to obtain, in this case, the complete reports for the project. So the user can go to the job data report. This is a very general report. In general, this the most general and in the most useful to communicate the different characteristics or features of our project and the calculation and the model. So here we can obtain the loads considered, the limit states, the combinations. We can obtain the different characteristics of the material applied now in the project, the geometric position of the columns, dimension and characteristics of the slabs. Okay, so in general, this is an incontrovertible report. We need to obtain this report in order to communicate the characteristics of our model. Others interesting reports. So in this case, I don't mention it, for example, columns and beams, but we have the focus in the slabs. But remember that you can go, for example, for the different beams, and we can edit a beam. We can obtain here the different reinforcement for the beam. We can obtain, for example, the different forces, plan view of the frame, the center of the beam. We have the possibility to obtain the different verifications. We can modify the reinforcement that the software suggests or obtain after the design. The user can modify these characteristics, not only the longitudinal one, but the transversal one too. Okay, same that the user can apply, for example, openings, vertical and horizontal openings for the different beams, and the software will verify and check that this opening with this opening, and the reinforce apply for this opening, the beam will check all the articles of the code. We have the possibility here to obtain a very complete report of the different checks article by article of the code. We can view the complete listing here. We can export this report to different formats: PDF, docx, HTML, etc. So all these reports are available at the end of the calculation and design of the elements. For the different columns, we can obtain a menu, a similar menu, in order to edit the different features for the section. For example, the longitudinal reinforcement, the transversal one too. The user can obtain, for example, the forces for the columns for every load case or combination, section by section. And we can obtain a 3D view. We can also export all this information to different formats. Okay, so it's a very, very interesting way to communicate the results of our project. And we obtain to the code checks in a similar way that we obtain the checks and the report checks for the beams. We have, for example, for a column, the different floor, the different groups, the section applied, the characteristics of geometry, backlink length, material, longitudinal, and article by article. The checks apply for the section in order to check the different factors of the code. So this is the work that the user can obtain for the beams and columns. Remember that we are focusing the attention of this presentation in the slabs. So in order to obtain the other reports, we have, for example, other interesting ones with the job takeoff. That is a very, very interesting report. We can see here the floor by floor, the area of farm work, the surface of the project, the volume of the concrete, the the bars, the weight of the bars, the necessary bars for the reinforcement of the concrete reinforcement, and the strands. Okay, in this case, the strands apply for the post-tensioned cables. So we have here floor by floor the information of all these classified by different elements: waffle slab, drop panel base, flat slabs, beams, columns, and we have all this information in order to have the necessary information to take decisions for the consumption of the materials and the economic characteristics of our projects, obviously. And here at the end of the report, we have the total job with the summatory of all these quantities for the total of the project. And we can obtain, for example, in this case, the drawings. We have different drawings. We can obtain, for example, the drawings of columns, all columns, all floor selections, and column detailing at all the eight of the floor. We can accept here. We can, for example, add the frames drawing. We can change the scale. And we can add the reinforced layout and takeoff summary. We will see here the aspect of the different drawings. The columns, all the information, all the necessary information in order to obtain and to present the project. We have the beams, and here we have the diagram to send the information to the for example, automatic an automatic fabrication, for example. Okay, so we have been talking about the to focus the presentation in slabs. So we will present the slab information. For example, here we will obtain the layout for the first floor. We have, for example, here the position of the reinforcement. Okay, this is the punching shear reinforcement with the traditional check. Remember that we have the punching shear reinforcement here for the 3 first columns and the detail of the reinforcement. Okay, and we have the checks and the reports in the other menu. So to obtain the floor plans and post-tensioned elements, we have the group selection. In this case, we will see the first one. We will see the different different kind of information that we can obtain floor by floor, taking into account the kind of a slab, the different kind of a slab that we have working with. For example, here we have for the first floor flat slab, we have the groups. Remember that we have different groups for this direction of tendons, symbols, stand area, etc. And we have here the distributed tendons in the other direction. We have the different points with the position of the cable of the tendon, of the tendon from the bottom of the slab. We can obtain, for example, for the floor slab, and we can add the passive reinforcement for the first floor. We need to add all this information to define completely our project. Floor front, all these drawings can be exported to different formats. Okay, so I have the floor plan, the layout, the punching shear reinforcement, the post-tensioned tendons, and the different position of the passive reinforcement bars. We can see. So the reinforcement of the punching shear, the classical one, the longitudinal at the bottom of the slab, the reinforcement for the bottom of the slab, but this one, the transverse one, transversal on the top, but longitudinal, and here the information of the tendons of post-tension elements. So we can print all these elements, and I will try to show the aspect of these plans in a classic CAD program, as I try to show how the kind of information that you can obtain and the save of time that you can make working with the program. All this information is obtained at the end of the calculation and design with the program. All the information is in different layers, so plotter or edit the plans are very, very easy. And you can see the information of the tendons and post-tensioned values. Okay. We have some information that in this case is not, I will okay, so we can see that the tables have the name of the columns, and all is very, very complete. Okay. So for the next, for the different slabs, we have more or less the same way to obtain the information. For example, for the we can see the layout, for example, for the fourth floor, the reinforcement layout, takeoff summary, and we need to add, in this case, the post-tensioning for this group. Okay. We have here the reinforcement of the in situ joist. Here the position of the different tendons, and here the information of the position of the tendon for in order to obtain the layout in the reality of the project. Okay. So I think it's mm, uh, more or less the all the information that I can want to share with you. We have an very interesting tool to to mm, work with. It's a very useful program because it's on not only specialized in the post-tensioned elements but we can also carry out the analysis and design of the all the elements of the project, so we don't need to pass from a software to another software to pass values and results and go and come back from different applications in order to obtain a final result for our project. In only one software, we can obtain all this information that is very useful, and we can save a lot of time working with the software to obtain the necessary information for a project. I can see that we have different some questions. I can try to answer the questions in a fast way. Somebody asked about the Indian code. We have the Indian code, but not the post-tensioning code. If there are a post-tensioning code for the India, maybe some of the checks have be applied by the user. For example, I know that some codes applied a limit for the distance for the tendons. In this case, for example, the software don't apply doesn't apply the limits for the tendon, the distance between the tendons. So it's the users that need to know these limits and apply the distance between the tendon in the right way. If we can hollow the core slab with a drawing, yes, we can apply some hollows or service hollows for the different slab in the different way. We have the a specific tool for that, and we can define a hollow defining a perimeter of beam and go to this tool that is the LED panel and empty the perimeter. Next one, we can somebody ask about the tendons and at the beams. Yes, we can pass tendons by the beams. The only way that the software permit or allow that a tendon pass by a beam is when an slab and a flat slab is at the both side of the the beam. So in this case, if I introduce here a beam, I can apply at this beam a tendon 2. Next one, if we have any movement and join or avoid an slab region, how we can model the void. If we have a join, it's necessary to define a limit and empty the area between the two neighborhood slabs. We can download hands-out. Maybe I don't know if you refer to the information, but we have here in the program the possibility to obtain information with a manual, a calculation, examples, and we have in our web, you can download our the program, the complete program, and there are an evaluation version that you can use for some days freely. It is possible to rotate tendons by 45 degrees. If you are talking about apply the tendon in this direction, yes, we can only to apply this direction for the direction of the tendons. Can we generate shop drawings for tendons? The drawings, I think I have shown the drawings where we can see the calculated losses report. Here in the reports, we have the reports of post-tensioning, and we have all the information about the different elements applied floor by floor, and the characteristics of the forces applied for our project. Okay. This report can be exported in different formats and take part of the project. Okay, so I think it's the goal or the main goal for this presentation is accomplished. So is to show the kind of tools that the user have available in the program to work with the post-tension elements. So, and remember that we have an support technical support team that you can ask questions or doubts. Don't hesitate in send us mails. So I thanks for your attention, and I hope that the presentation will useful for you and for your professional task. Thank you very much.